Hello, I'll continue with this topic on radioactive decay. So previously I was talking about how in this example, using say cobalt 60 as the radioactive source, if we measure the activity of the source in terms of how many say gamma photons are detected by a counter every minute, and if we plot the graph against time, we'll find a graph that looks like this. It comes down in a curve with a very special property that after every a certain period of time, when the particle the activity comes down by half, we'll find that if we wait for the same period of time, the activity would come down by half again. So it always comes down by half after the same period of time. Now this period of time would be different for different radioactive source. Now in this video I want to describe the explanation for this behavior. Now and at the same time, let me also mention that if you actually plot the graph, what you find is that it's not going to be a very smooth graph. It won't be a very smooth graph. In fact, the actual points that you would find sort of goes up and down along this curve. So this point might be maybe a bit higher, that point might be lower, that point might be higher. So it sort of jumps up and down a bit with quite a bit of error, it seems. But as I explained, this is due to the nature of the emission of the radioactive decay. So it is not an error in the measuring instrument. So there is this random nature of the decay, and then there is this special property of the half-life. Okay. So if we think about our radioactive material, I'll just call it in general a radioactive material. So if we imagine that in this material there are lots and lots of atoms, of course. Now if I look at a particular atom, if you can actually see it, we might imagine, just staring at one particular atom to see when it would decay and emit a radioactive particle. It doesn't have to be gamma. Let's say in this case I look at an example where it emits say an alpha particle. So if I look at this atom, right, this atom, when is it going to emit an alpha particle? Well, we have no idea. If you look at a specific atom, there's no way to tell whether it will emit a particle now, or in a minute, or in an hour, in a day, in a month, or in a year. It's completely random. It can just happen now, or sometime, or never, or at least or not in our lifetime. Okay, and that's what happens when you look at a particular atom. But if you look at a large group of atoms, you'll find that there would always be a certain average number that will decay, that would emit a particle every second or every minute. So there's always this average number, but it's just that we don't know exactly which one. So for example, if I have, let's say, maybe, for example, I have 100 atoms. Okay, let me be more precise in my terms. Let's say I have 100 nuclides. Okay, 100 nuclides, the specific nuclei of this radioactive material. If I look at this 100 nuclides, all right, a group of 100 nuclides, I might find that on average, every 1 second, let's say, one nuclide would decay or would emit an alpha particle. So one decay per second, for example. So meaning that it can be any one of the 100 nuclide that decays. We have no idea which one. Alright, if you just look at one, there's no way you'll know whether it will decay. But it's just that if I look at 100, then and I know that on average there'll be one decay per second, then what you would find is that most likely, every second one of these will decay. But you don't know which one. Alright, it's in that sense it's completely random. But one thing that is not so random is this average rate of decay or the activity, and that is fairly constant. So if it decays, if it's one decay per second for say 100 nuclides, then one of them would most probably decay, would be very likely to decay, even if you don't know which one. So it's a kind of a probability thing. It happens by chance, but the average is kind of fixed. So it's a bit like you know, when you wait for a bus, all right? You will be waiting and hoping that it will come in the next minute, but you might be disappointed, and then you hope that it'll come in the minute after that, and maybe if you're lucky it will come, but there's no telling which minute it will come. But you kind of know that it will come because the bus is supposed to follow a certain timetable, all right? So it has to come, but you can never be sure exactly when it will be, exactly at which second it will come. So in that sense, there's this randomness involved. Now, in this case, let me look at this example a little bit more and think about it in terms of a probability. If it is actually one decay per second for every 100 nuclide, then it means that in 1 second, okay, the probability let's see, probability, okay, that a nuclide decays, right, for this example, yeah, is equal to 1 over 100, or 0.01. So in this example, we can say that this is the probability that a nuclide would decay. But if you look at a specific nuclide, like I said, you won't know whether or not it will decay in the next second. Okay, just as you know, when you toss a coin, the probability that you get a head is half. But if you actually toss it, alright, if you actually toss it once, you won't know whether it will be head or tail. Alright, whether a coin will give you a head or a tail when you toss it. So it's that kind of idea. Okay, so taking this idea a bit further, we can actually write down an equation. We can actually write down an equation and eventually derive a formula which shows that it follows the feature of a half-life. But um, before going there, let me just mention that this description, okay, can actually explain the random nature. All right, this probabilistic behavior can actually explain the random nature that I described earlier on, of the decay. Right, it explains why when you actually plot a graph, when you actually measure the activity, there's a lot of apparently a lot of randomness involved when you measure the activity, the number of decay every second. It sort of goes up and down quite randomly, right? Although it always follow a certain average. Okay, so right. So let's take this idea a little bit further. Suppose now that the the total number of nuclides in this material is n. Okay, suppose that there are n nuclides altogether. So in 1 second, therefore, the number of decays in 1 second would be, let's see, so I was saying that probability is 1 over 100, and we know that if there are 100 nuclides, it's 1 decay per second. Now we can think of this 1 decay as coming from 100 times 1 over 100 to give 1. So if the probability is 1 over 100, then if I have n nuclides, the number of decays must be 1 over 100 times n. Okay, so 1 over 100 times n. Now, what I can do now is this. I can now think of this in terms of the activity. Okay, if I divide this number of decay by 1 second, I divide this by 1 second. No, I don't actually do that. Let's just do it in a simpler way. So since this is the number of decays in 1 second, it means that it's actually the activity that I was talking about. So this is actually the activity, right? That's what it means. That's what activity means, number of decays per second. So therefore, I have an equation which says that the activity is equal to 1 over 100 times n. So this relation is an important relation. It gives us it relates the activity, the number of decays per second, to the total number of particles, and this number that multiplies by the number of particles is, as we have seen, the probability that a particular nuclide would decay. Okay, so now that we're here, let's take this a little bit further and see where it leads us. Hopefully it will lead us to the graph that I described just now. Let me clear this up. So now going on from here, what we'll find is that what we can actually solve this equation now. Okay, now if you have learned calculus and differential equations, you'll know that the activity, number of decays per second, we can think of the number of decays per second in terms of the rates of change of n. Okay, so rate of change of n, we can think of it as rate of change of n. It can be written as dn dt in calculus. So and we can think of this as the increase in number of particles per second. The increase in number of particles per second, the rate of change. Now we can relate it to the activity if we understand that the number of decays in 1 second is actually the rate at which n is decreasing. Okay, when we say the rate of change, by default we mean the rate of increase of n, but the number of decays in 1 second is actually the rate of decrease. Alright, so the activity here is the rate of decrease of n. So that's what it means. Okay, so therefore A is actually equal to minus of dn dt, because decrease and increase are opposite. So if we think of dn as the change of n in a short time dt, okay, then a decrease would mean that dn is negative when we take, say, the final n minus the starting n. Okay, so if dn is negative, then we have to put a minus sign so that this becomes equal to so that this becomes positive, and then we can compare it with a, which is the rate of decrease. So since this a is actually minus dn dt, I can write down a differential equation now. Minus dn dt is equal to 1 over 100 n. And this can actually be solved for n. I shan't go into the details, the detailed mathematics of how to do it. I'm just going to write down the solution directly. So the solution for this equation would be n is equal to n naught times e to the power of minus 1 over 100 times time. Okay, now if you're seeing this function for the first time, it can be a little bit abstract and rather difficult to understand why this is what you would get when you solve this equation. So if hopefully you have done learn this differential equation, you would have already known this answer. But if you have not, that's fine. We could just accept this as the answer, the solution to this equation. And the important thing here is to try and understand, try to become familiar with this function, and see how it relates to the graph that I showed just now. Okay, so right, so let me now explain some of this physically, starting by E. Right, let me start with E. E is a number which is equal to 2.7 something. Okay, I shouldn't try to remember that. Something that you can get from your calculator, in which is actually is usually labeled EXP right next to one of the buttons. So meaning that we can let's say if I have e to the power of x, this number to the power of x, it can also be written as exp bracket x. Okay, so these are the kind of notations. So e is actually a number 2.7 something. So it's actually a number to the power of this, where t is the time, right? As we know, n we also know is the number of particles. But what is n naught? Well, n naught actually is the starting number of particles. Is the starting, or the starting n, if you like, the starting n. As time passes, n would change. We would expect n, the number of nuclides, to decrease with time. And indeed, if you plot a graph of this function, you'll find that n decreases. This is e to the power of minus number times t. So it's a negative power. So if t gets bigger, we have a bigger minus sign of power. So therefore, this function must give you a smaller and smaller answer. Okay, and you'll find that if you plot this graph, you would indeed get something that looks the same as what I showed just now. Let me clear this. If I plot a graph of this n against t, you find that when t is 0, we have e to the power of 0, and we'll get so e to the power of 0 is 1, so n is just n naught in the beginning, which is, as I've described it, is at the starting n. And as time passes, as t increases, this will come down, and it will come down as a curve, right? You see, as t gets bigger and bigger, this function will get smaller and smaller. So the graph would come down, but it would be a curve. It wouldn't come straight down. This is not a straight line equation. And it'll get closer and closer to 0, but never exactly going to 0 as this function behaves. And you'll also find that if this is the answer, if this is the answer to this equation, it would also have the property of a half-life. Okay, so I shan't go through the mathematics to prove that, but I would just state that, I would just mention that this function has the property that after a time, let's say after a time when the starting amount becomes half the value, right? Let's say the time, I'll call that time t subscript half. Right, let's say after a time t half, the starting amount come down by half the amount. Then you'll find that after the same time t half, meaning the time would be 2t half, this amount would come down by another half to become 1/4, and so on. Okay, so this is a behavior that this function would have. So assuming that we accept this result, it means that this function actually matches, all right, actually give answers that agree with what we would observe by measurements. Now, and this is important. This is important, an important result, because it also means that um, our idea, if you remember how we got here, our idea that the number of decays in 1 second is the probability. Remember what the 1 over 100 means? It's the probability that a nuclei decays in 1 second. So when if we describe this as the probability, we are actually when we describe this as a probability, we actually made an important assumption. All right, that each particle, each nuclide would decay randomly, completely by chance, and that it has a fixed probability of decay. Now that's actually an a rather, if you like, a rather big jump in imagination, because after all, uh, we can't even see the atoms, right? We know nothing about it. So saying that an atom should behave in this way, and to have such a probabilistic behavior, is actually a big assumption. Okay, so this whole calculation here was a big guess, if you like. But the fact that it turns out to agree with the observed, the measured behavior, the measured graph, confirms that this understanding is correct. That is actually is actually okay. It's actually right to think that um, each atom, each nuclei has a fixed probability that it will decay in 1 second. So this agreement tells us that this is true, and gives us an important and useful understanding of what goes on in each atom. So now that we have a clearer understanding of this, let me finish up by doing maybe two things. Okay, let's just quickly do this. Now, what I would like to do is to make this formula a little bit more general. So the 1 over 100 probability was something that I just plucked out of thin air. I just made up a number. So in general, in a real radioactive material, it doesn't have to be 100. In fact, it would be different for different materials. It's just that for all materials, it has been observed that they follow this behavior. Okay, so what I'll do is that instead of calling it 1 over 100, let me replace this by a symbol, lambda. And lambda is the symbol that's often used. So I would write this. Let me rewrite this as A over lambda n, where lambda is the probability that a nuclide decays in 1 second. So my equation is now A over lambda n, and this equation now becomes minus this equation minus dn over dt equals to lambda n. So I replace the 1 over 100 by lambda, so that I can also use it for other radioactive material. And therefore this solution would be n is equals to n naught e to the minus lambda t. Okay, and so that's one thing that I want to do. Now the other thing that I want to do is to let's see. All right, is to express this in terms of the activity. So what you'll find is that if I now substitute this, if I now substitute this into here, okay, let me do that. Let me substitute n, the n equal to this into here. So if I do this, this is what I'll get. And also substitute right, a equals to and replace this by a again. If you remember, dnd minus dn dt was supposed to be a. So replace this by the a again. Okay. And substitute this. Okay. Replace this by a. No, let's see. Let me start again. Sorry, it's getting a bit confused. Okay, what I'm going to do is I'm just going to use this directly rather than jumping over to here again. So that's what I want to start from. Okay, I'm going to say that, right, this is a, right? This was what a means, as we have seen. So I'm going to replace this by a. Replace this by a again. Okay, let me make it even simpler. Let me just go right back to the start and start from there again. That's just a. So I'm going to write that down here. That's just a. And is equal to lambda n. Okay, is equal to lambda times n. But n is actually this. Alright, the n here is actually equal to n naught e to the minus lambda t. So that's what I'm going to do here. I'm going to replace the n there by this formula. So this is n naught e to the minus lambda t. Okay, and then I'm going to say that n lambda, since we know that the activity is lambda n, lambda times number of particles, so lambda n naught is also the activity, but since n naught is the number of particles at the start of time when t is 0, so lambda n naught should be the activity at the start as well. So I can call this I can call this a naught. Alright, I can call lambda n a naught. So I have an equation now for the activity. I have an equation for the activity. Okay, so let me replace this by a naught, and the equation would now look like okay, I'm running out of space. Let me try and squeeze it in here. I have a is equal to, let me use a different color. So this would be a, and I'm saying that lambda n naught is a naught because lambda n is a. So lambda n naught is just the a at time t equal to 0, which I call a naught. So a is a naught, and that's just the same. I'll just copy it over, e to the minus lambda t. So I have an equation for the activity as well, which has exactly the same form as this. See, that's an equation for the number of particles, and this is an equation for the activity. So same form, except that the n is changed to a. Okay, now, and this means that if I plot a graph of the activity, it would look exactly the same as it would have the same shape, the same kind of curve as the graph for n. So that means instead of n, I can also use say a. And in fact, a is the activity is what was actually measured and not the actual number of atoms. Okay, so, and as I've already mentioned, this curve agrees with the measured graph.